In this video, we're going to take a look at the Spectre exploit and discuss how it leverages speculative execution and other hardware behaviors to create a side channel that can leak sensitive information. Spectre takes advantage of speculative execution by training the CPU's branch predictor to guess incorrectly. We've already seen how the CPU can execute instructions out of order during normal operation. But what happens when speculation encounters a branching instruction, such as a conditional jump? Well, it turns out the CPU has a dedicated subcomponent that's known as the branch predictor. And as the name implies, this component's responsibility is to predict whether or not a branch will be taken or not taken during speculation. Broadly speaking, the branch predictor uses two pieces of information to make this determination. The first is the individual branch history of specific instructions, which can be uniquely identified by their location in virtual memory. The second is the global branching history for all branching that has recently occurred on the physical CPU core. Now, this means that the predictor can be biased by repeatedly branching in a specific direction. Branch predictors work by encoding whether or not a conditional jump instruction is taken or not taken as 0 or 1. This means that for any given branching instruction, a corresponding branch history can be represented as a sequence of zeros and ones. These zeros and ones are then passed into a state machine inside of the branch predictor that corresponds to that specific conditional jump. The state machine's output represents the prediction for that particular instruction. These state machines are typically pretty small in size, only consisting of 4 possible states, or 2 bits. The reason for this is by having a 2-bit counter, or 4 possible states in the state machine, an immediate deviation from the expected behavior does not immediately change the future prediction. Despite its simple appearance, this state machine can correctly predict a number of branching patterns that are commonly found during execution. This information can be used to influence speculative execution by poisoning the branch histories that the branch predictor relies upon. Keep in mind that the branch predictor operates on a per physical core level. So when training a branch predictor, the execution needs to occur either in a single process, possibly in different contexts, such as kernel or userland, or in multiple processes that are on the same physical core. In many cases, mistraining the branch predictor does not take many runs to start showing results. Spectre attacks train the branch predictor to cause speculative execution to run instructions that may not have otherwise ever occurred. In this video, we're going to talk about the 2 initial variants of Spectre that were initially disclosed. The first variant takes advantage of conditional branches. The second variant takes advantage of indirect branches. Another important property that makes Spectre attacks different than Meltdown is that Spectre attacks occur inside of a victim process. The code snippet above is a minimal example where Spectre V1 applies. In it, we see that the variable x is first checked to make sure it is smaller than the size of array 1. Assuming that it is, x is used to index into array 1. The resulting value is then used to access array 2. Now, thinking about this block of code concretely, it should never execute if x is greater than array 1 size. Spectre V1 relies on the fact that the CPU can speculate that it does. The first step to make this occur is a training phase. During the training phase, the conditional jump instruction is executed with the same result repeatedly. Now, this could occur because an attacker is influencing the behavior of the program, but it also occurs during normal execution. If this snippet of code during normal operation is always ran with a valid x, then the branch predictor would always expect to execute the inner block of code. Once the branch predictor has established this pattern of always running this inner block of code, if speculation occurs with an invalid value, then array 1 will be accessed with an invalid index, resulting in an out-of-bounds memory access into transient instructions. So if during normal execution we have array 1 of x, That value could be, for instance, 0, 1, or 2, we see on the right-hand side. But if we give it a very large x, like x equals 1,000, this could be far beyond the bounds of the array to where what we are accessing is actually a private variable that was never intended to be used. So to summarize Spectre V1, if array 1 size takes a long time to access, or there's some other slow-running instructions above this conditional jump, the CPU will speculate. And when the CPU speculates, it has to predict whether or not to take this branch. If it incorrectly predicts the branch, the instructions that were executed speculatively are transient instructions that never executed concretely. But we do know that transient instructions can influence the cache. In fact, if we look at that pattern that was inside the conditional block, we've seen it before. This leaks information via the cache that can be read via flush and reload. Now, I do have a demo that kind of runs through this, so let's see it in action. The first source file that we're going to look at here is not the exploit. This is the victim code. And looking at the victim code, the first interesting thing that happens after main is called is set affinity. What set affinity is doing is pinning this process to a specific CPU core. We need this because, if you'll recall, Spectre relies on manipulating the branch predictor, and the branch predictor operates per physical core. And so we want to make sure that the process that we are exploiting, as well as our exploit code, are on the same physical core. The next two lines are moving values into a guarded array and a secret value here. We then see that the challenge opens up shared memory. We can take a quick look at this, but all that's occurring is we're creating a shared memory device, and then we're M-mapping that into the process. Now, the way that you interact with this particular challenge is via that shared memory. Index 0 indicates whether or not it should run. Index 1 is an index that determines what this challenge is going to do. And then index 2 is a flag that will cause the program to exit. If we look at the kind of main run loop here, while the do exit value is not set, a run value is checked. If run is 0, it will just busy loop. If run is set, we break out of the busy loop, clear run, and clear index. We'll get the index value from shared memory. There is some slow operation here. In this case, it happens to be some more floating point math. We then have a conditional check if the index is less than 128. Now, why 128? Well, 128 is the size of our guarded array. We see right here, guarded array length, which is 128. And so what this is doing is this is creating a slow operation so that the CPU doesn't know if it should take this branch or not. And so it will speculate on that. And the branch predictor will return either to execute this line or not execute this line. It then loops back around to our busy loop. It reads in whether it should run, and then based upon that, it will either busy loop or run through the larger loop again. You'll notice that there is no synchronization in this particular challenge process. And so this is a very noisy program. If the only way to interact with it is essentially via hot bytes in shared memory, we do not have fine-tuned control as far as, well, how many times did this execute? Or how many times did it run on a particular index? I wanted this example to be something that has a lot of noise so that we can see that you can deal with kind of less control inside of the process that you're exploiting. And you'll note that inside this conditional check, the line that is being executed has that familiar pattern where we're accessing array 1 and using that value to access array 2. Array 2 is the shared memory that is being mapped and used as the communication channel. This is important because we're going to try and leak this via a side channel, via the cache. Well, in order for a cache side channel to work, your exploit code and the victim code need to be accessing the same underlying physical memory. And in this case, since this program communicates via shared memory, this shared memory, when the victim process is mapping it, and this shared memory, when the exploit code is mapping it, both point to the same underlying physical memory, which means we can use this shared memory space for our cache side channel attack. Now let's look at the exploit code. The exploit code looks a lot similar to kind of what we've seen before. We still have the same functions that we've seen: post inner work, post work, inner work. There is a flush and reload going on. There's some pre-work. So this is a similar pattern to what we've already seen. Now, if we look at main, what is the exploit code doing? Well, the first thing the exploit code is doing is it calls set affinity. This set affinity is the same code where we're pinning the exploit code to a specific physical CPU core so that it will interact with the same branch predictor as the victim code. Next, our exploit code is attaching shared memory, which is doing that exact same thing that the victim process did. Now, when we init our exploit here, we want to set the communication values in the shared memory to be a known state. So we're going to set all of them to be 0. Within my exploit code, I'm going to start the target, start the victim process. And we see that I'm doing that by just calling fork and exec. After I've started the process, and in other places in the code, you'll see this schedule yield. What this is like a micro sleep. This is the process stating that the CPU is free to execute other processes on this core. And so this is like equivalent to doing the smallest type of sleep that you could to allow other work that is scheduled for the CPU to occur. Because all of this, my exploit and the victim process are running on the same core, along with any other work that needs to be done, we want to make sure that the CPU has ample opportunity to context switch between the different processes running on the core. Now, once the victim process has been started here in start target, we schedule yield so that hopefully the target or the victim process will have the opportunity to run. Once it's running, we call this exploit function. This is kind of where it gets messy. So this is, again, a kind of modified way of looking at that same data. We're using a flush and reload. I've modified the way that we're checking this to be a little bit more smart for some of the problems that exist in this specific challenge. So while we have unsolved results, we are going to perform a loop. For every character, for every index into whatever length it is that we're trying to leak, if the result is unknown, or the result is known, then we'll continue this loop. We'll go and look at the next character. Because our unknown representation in this results array is null. So for every character, we're going to clear the stats, or for every index, we're going to clear the stats data. We have no information about this index for this run. If we know all values, then let's break out. But we're trying to leak a particular index. This right here is the work loop. Now, the work loop looks very similar to what we've seen elsewhere. We have pre-work and we have post-work. What's different is I have now this train target, and I have an additional pre-work, and then I have speculate. So what we used to have was pre-work, some type of memory access, then post-work. Let's take a look at what is happening immediately after pre-work. Well, first let's just recap what pre-work does. Pre-work is just flushing everything that we're interested in from the cache. Still doing the exact same thing. Now, what is train target? Well, this challenge code, if we look at it, it doesn't have like a default behavior. So we have to put in work as the exploit to get the branch predictor to want to execute this inner loop. So in train target, we are writing a valid index, and we're again kind of looping through here because we don't want any prefetching to occur to impact our cache results. I don't believe we'd have to do this, but I am, because I am always wary of side effects with prefetching. But what we're doing is we are repeatedly allowing the victim code to loop with valid indexes. We see that the index that I'm setting it to is modulo 128, and every one of these values that are read in while it's running will be a valid index. Now, this doesn't mean that the program's going to run 1,000 times. This 1,000 is somewhat arbitrary, because remember, we're communicating with it via shared memory with no synchronization. So I actually don't know how many times this is going to execute in that while loop. That's going to just kind of be based upon how busy the core is. And so I don't have a lot of fine-tuned control on how many positive branches occur versus how many negative branches occur. I just can force it to see a large number of positive branches inside this conditional check. And that is what I'm doing with this first loop in train target. In the second loop here, I am trying to set it so that the run value will be set to off. If we look back at the victim code here, we see that index 0 is whether or not it should run. And the problem here is that I don't know if the challenge program has actually stopped running on valid indexes. And I want to provide some type of a pause here so that I know it's done running on my valid training values. Once train target is done, we run pre-work again. Now, pre-work is flushing the cache. The reason that I need to flush the cache a second time is because when I'm running the training, I am interacting with the cache. And I want to make sure that the training data doesn't get mixed up with my measurements when I am performing the exploit. And so I'm flushing before training data, or before the training run, and then I'm flushing again after the training has completed. Once I believe I have the victim process primed up from running all of these valid indexes, I'm going to run this speculate function. And speculate looks very similar to train data. Speculate is going to constantly write to that shared memory with an index that I am interested in that is beyond 128. And then it's going to be setting the run value to true. And then we schedule a yield, right? We release execution because we want to allow the victim process to hopefully access the shared memory that we're writing and then perform a loop of execution. But we don't have any guarantees that that is actually occurring here. After we have performed the speculation, we do post work. Post work, again, is doing a summation of how many entries did we find and trying to infer what was the value that was placed in the cache based upon what we just did. And so once we have done our post work, the stats value or the stats array has been loaded with information that we've observed from these executions. We review the data from 4,000 loops here. For me, 4,000 was necessary because this is such a noisy environment where we may or may not observe what we need. I needed to have a large number of sessions here of training and then observing and then training and observing, because the instance where I do capture a value in the cache is actually quite rare. This will not necessarily be the case in the challenges on the Dojo, but it is the case for this very noisy example. So once we have all of our stats data loaded, we try and infer what is in the cache based upon the observations, and we'll print it out. And we'll do this in a loop. So let's compile this. Here I have a build sh since there's 2 files. And if we run Spectre demo, what we see is I'm getting cache hits, but we also see invalid values. We see there's quite a bit more noise than we've seen in prior examples. Well, we see a lot of 112 in the data. And so I'm inferring that that implies the value that I'm trying to get there is 112. But we see there are other values that are showing up in the cache data. And the reason for that is because even though I have a flush after my training, this isn't perfectly synchronized. This is a noisy environment. So I may be flushing, but that doesn't mean that the victim process is done executing. So I may be flushing values from the cache, and the victim process is executing and accessing some of those values all on its own. And so in order to kind of improve my fidelity, I'm doing a large number of executions, and then I've also set a threshold on how many entries I must observe before I will consider the value the correct value. But we do see that despite the fact that I do not get to directly control execution in the victim process, and I don't get to, for instance, trigger the victim process to execute like one at a time. So I give it A and it runs, or I give it 1 and it runs, then I give it 2 and it runs. I'm not allowed to like get this fine-grained control. This is actually quite chaotic, and you shouldn't code like this with hot bytes of shared memory that are being accessed by multiple processes with no synchronization. Like, it's a horrible programming practice, but I think it demonstrates that despite being a very noisy and chaotic environment, you can kind of find the signal that you're looking for despite the noise that's going on. It's just a matter of fine-tuning your parameters and making sure that you are getting enough measurements to where you can reason about what is noise versus what is the signal you're trying to create. Now, everything we've discussed up until this point, it refers to Spectre Variant 1. Spectre V1 takes advantage of conditional branches. Spectre V2 works in a very similar manner, but it is focusing on indirect branches. Here we see a minimal example where Spectre V2 may apply. The purpose of the first instruction is to simply be something slow that encourages out-of-order execution or general speculation. The kind of critical component are the next 2 lines. On line 2, we see a constant memory address, dead beef, being loaded into RSI. In the third instruction, RSI is being dereferenced, and whatever address is stored there will be jumped to via the call instruction. If we were to word this in another way, we could say that the CPU needs to go out to RAM and access the memory address deadbeef. Then retrieve the value that is stored there. Whatever value is stored there is where this call instruction will jump. So the value that is stored at deadbeef may not be in the CPU cache, in which case this is slow, and it is something that could be speculated against. Very similar to Spectre V1, where there was a branch predictor, the CPU has a predictor for indirect jumps as well. And this indirect jump predictor can be trained. And by training it, we can cause arbitrary instructions to be executed as transient instructions if we train it to predict incorrectly. Now, an attacker that's trying to take advantage of Spectre V2 faces some additional constraints compared to Spectre V1. One of those is that it doesn't make sense to try and influence the program to jump to a completely invalid address. That would just cause the victim process to segfault and exit. So what the attacker should try and influence the branch predictor by causing this jump to go to a valid address. Now, it may be a valid address in a different context, but it needs to be a valid address where execution can continue. An example of this is two virtual addresses that map to the same physical underlying address. It shouldn't matter from an execution standpoint whether or not the instructions are accessed via one virtual address or another. The branch predictor will pick up on these new jump targets and begin to predict the new locations. Ultimately, it is the attacker's goal to execute something that's referred to as a Spectre Gadget. Now, we've seen Spectre Gadgets throughout this module. Spectre Gadgets are any set of instructions that, when speculatively executed, influence the microarchitectural state in a manner that communicates information via a side channel. So we saw a Spectre Gadget in the example in this lecture, in C, as shown on the left. But Spectre Gadgets could also exist in the raw assembly via something that looks like the example on the right. If the attacker can influence RBX or RDX, then the attacker can change the address that is speculatively accessed by the dereferencing of RDI. And by doing that, it will influence what value is loaded into the cache, and this communicates information about the value that is stored at RBX plus RDX. There are many variations of the Spectre attack nowadays, and there are many variations of hardware side channel attacks in general. Some of them only exist in theory, where a particular edge case should exist, but we haven't been able to prove it. Other times, you may find a real-world proof-of-concept exploit that works on a specific model of hardware. In general, you'll find that all of these kind of exploits follow a very similar pattern. First, try and encode the secret data that you're trying to communicate or leak within the microarchitecture. In this module, we targeted the CPU cache, and you'll find, if you look at other variations of hardware side channels, the CPU cache is frequently used for this purpose. Next, try and retrieve the embedded data via the side channel. Now, we used flush and reload in this module, and flush and reload is used in a lot of other side channel exploits as well. However, there are other ways to embed information in the CPU cache, where flush and reload is not the only way to communicate information via the CPU cache. Hopefully, this discussion has lifted some of the mystery and mystique behind these big name exploits that on the surface appear to be black magic.